Hi, my name is Paula Alarcon-Espejo, and I'm a PhD student in Material Science and Engineering at the University of Kentucky, and I'm working here in Organic Electrochemical Transistors based on PEDOT PSS fibers. Organic Electrochemical Transistors are also referred as OECTs, and as any other type of transistors, they are like on-off switches. OECTs can obtain mechanical, thermal, electrical, chemical data from different environmental stimuli, and they are also biocompatible. The human body contains a lot of information, and having these devices in clothing will help us have different computer fabrics that will enable us to obtain, analyze, and return different digital health insights. In the lab, we're going to see a fiber-based OECT, and it's composed of two electrodes that are called the source and the drain, and then the active material that is going to be placed on both of them. In this case, we're going to use the PEDOT PSS fiber as the active material in our device. So what is going to happen is that there's going to be a flow of charge carriers from source to drain that is going to create an electrical response that can be tuned by the presence of ions from the electrolyte and also the gate voltage that is a third electrode we have. So these devices are made from a 3D printed stage. Then we will place the electrodes on top, the electrodes we choose for this device, then the PEDOT PSS fiber, and then we will use a paint or dispersion to make the contact between the fiber and the electrode. First, we have a 3D printed mold in which we are going to build the devices on top. So we have already two prepared here. You can see this is the electrode, we have the PEDOT fiber, and then we use a contact material to put the fiber in contact with the electrode. But I will build another one for you guys. So we basically grab the electrodes of choice. We place it as close as possible to the well or here. And then same for the other one. These are gonna be our source and drain later in the device. Okay. Now we grab our PEDOT PSS spool, the one that Ruben has already spun. We try to find the PEDOT fiber. Well, now we found the fiber, we need to take it out of the spool and then place it carefully on top of the electrodes. And then we'll make the contact afterwards. It broke. And now we need to make contact using the paint. And that will be it. Now we need to let it dry for a few minutes, and then we can measure the resistance to check if this device could work or not. Here you grab the two probes, and if our contact is stable and good, we will use the resistance of the fiber. And as you can see here, the device will be able to work, so we can test it and finish building our OECT. So now we're gonna take this upstairs to the Organic Materials and Devices laboratory, and we're gonna add an electrolyte and then test if this OECT works. So this is a microprobe station, and we're gonna place our device here to perform the measurements. And this microprobe station is connected to this equipment that is a precision source measure unit. And we're gonna put these two microprobes on top of the electrodes. One of them is gonna act as the source and the other one is gonna act as the drain. Okay, and now we're gonna add electrolyte, that in this case we're gonna use sodium chloride. Now that the electrolyte is inside the well, we need to put the third electrode, that is called the gate. That in this case we use a silver chloride pellet. Okay, and this is ready, so we can take measurements. First, before that, we can check in the microscope if everything is working. So here we can use this microscope we have in the probe station to check if everything is okay or seems okay to the eye. So you can see here our fiber, the electrolyte we put, the fiber is very swollen over here. So this is a good sign. And then we have our electrode, our contact material over here, and this is one of the probes we are using. And you can see slightly the gate electrode over there too. So with this equipment, we're gonna obtain the voltage current characteristics of this device, and this is what is called a transfer curve. So what you do here is measure the drain current while varying the gate voltage at a specific drain voltage. So I already have the parameters over here I'm gonna use for this device. And now if we graph it and play it, the device starts at an on state, and then while we apply a gate voltage, a higher one, we're gonna turn the device off. That it would be over here. This is in a linear region, and then the next curve is gonna be at saturation regime. So over here is on, and then as you can see, is turn it off. And from here, we can extract a lot of parameters for this device. Now that we've seen the voltage current characteristics of this device, we also do a transient method to obtain mobility for these devices. So what we usually do for this one is apply a gate pulse, so a current that you input to this device, and then you measure the response time of this device. So here, for example, I will put a pulse of like 250 nanoamps. We have gonna use a drain voltage so that we can drive the device. And then this would be the response time of the device to reach the steady state. We need to apply this pulse multiple times, and then using the slopes of this plot, we can obtain mobility. Our main result is based on contacts, so we've discovered that it's very important to have good electrical contacts with the PEDOT PSS fibers, otherwise your devices are not going to perform as expected. We've also seen that PEDOT PSS fibers have very good thermal, mechanical, and electrical properties due to our stretching through the wet spinning process. So combining these contacts with the fibers will enable us to have very powerful and very fast devices. Our main discovery is that we've seen that our devices have very high mobilities, which is not very common in the field of organic electronics so far.